All right, welcome back again. What we are going to do as part of this lecture is explore the journey from text to binary. Okay, before we get there, some theory like always. So let me pull up the whiteboard. What I want to tell you is what we are going to do. So first off, we'll have an assembly file and we'll just have one instruction in it. All right, that's number one. That's step one. We'll not bother as much about the syntax of how assembly is to be written. We'll only bother about, you know, uh, the intention of that one line. And the one line essentially here is one instruction. Actually, we'll have two lines just because we'll separate them. So two lines, but just one instruction. Right? And the second thing that we do is then convert this into the machine code. And what we'll do is we'll use our toolchain. So we'll use GCC, the GCC for RISC, RISC 5. We'll use the GCC toolchain that we had downloaded in the previous lecture. We'll use that, and let me put myself here. So the idea then is we go from some text to zeros and ones, right? And a homework for you would be that we are going to print the zeros and ones, the content of this on the screen. And what you're now supposed to do is take that bit encoding, take that instruction, the memory content, and then try and figure out what that instruction is based on the ISA document. Okay, that will be a homework for you. All right. So now once we have this binary, so to speak, we are going to load it into QEMU and instruct it to run in kind of the RISC V 32i CPU mode. And then what we are going to do is GDB, take the debugger and connect to it. Again, this is very convoluted, but the reason I want to do this now is because over time it will kind of sink in and you'll become more familiar with this. And our focus then, in due course will come just on the C language and all these tools will fade in the background, right? That is my intention. So we are going to kind of GDB into this system, and then I'm going to show you a few cool things there. Okay, so hopefully things are clear. We are going to write an assembly file and then we are going to convert it into binary or machine code. Now, one thing I want to bring your attention to is we are going to use obviously GCC. A backstory about GCC is the front end. What does that mean? Front end means it's kind of the tool that can take in commands, and then internally it can call the assembler, it can call the linker. And again, what is the role of assembler, linker? We will come to all of that in due course of time. It's very hard for me to guide you on something by telling details of everything. So we are going to just trust the process right now and learn something about each tool a little bit. And over time, that the knowledge will compound, will add to our knowledge of each tool over time. All right. So I'll quickly tell you, and then there is a compiler. Right. So I'll quickly tell you as what the flow is, how things convert into different forms, right? And so we start off, let's say, with the C file in general. We submit that to GCC. GCC says, hey, I look at the C code, and at some point it is going to convert it to assembly internally. This is not visible to us. We can ask GCC to stop at the assembly stage, or at least after the stage where it has converted C language to assembly, and we'll explore that also. But then after that, it calls the assembler, the AS. In the tool chain, there was something that had -AS. So that utility it calls, and that utility converts the assembly into something called object code. And what object code is, we'll come to also. So object code is pretty much binary code with some holes in it. And then after that, there is linker that takes multiple object codes. Sometimes what happens is you have some recipe here that calls into the recipe into another object file. So the linker is the one which will kind of fill in those holes. There will be a hole like, okay, call X, but X is at what location? That's not known. So the linker is the one which will combine the object files and create the binary. Fair? So we start from GCC that converts it to assembly. Then there is assembler that converts it to object code. Then there is linker which converts the object code into the binary. Now, the reason I'm explaining you all of this, the fact that GCC calls into all these commands internally, is because when I execute the commands, you'll notice that I'm actually invoking GCC and not the assembler and the linker. But behind the scenes, they are getting called, right? That is the intention. Now, one other thing about linker that you must absolutely know, and when like very few people know about it, the ninjas must know about it. And you are a ninja, so I'm going to tell you. The linker is going to place the code and assign addresses to each instruction, right? So that that code can be loaded into the memory at the appropriate address. So someone needs to tell it as to what address the CPU is going to start to fetch or what address the memory starts at. Fair? So to be able to tell it that, there is a separate language, there is a separate scripting language called linker script. Linker scripting. So it's a text-based description that the linker can consume and understand that, oh, okay, you want me to put the code part here. You want me to put the data part here. And if you're not understanding this language yet, fine, we're going to get into it. Not a problem at all. But just know that it is going to take a file that ends in the .ld extension, and essentially using the object files and the linker script, it generates the binary. That is the whole point, right? And what I'm going to do now is go back to our working environment here, and I'm going to copy paste code from another window uh, just so that I don't waste time typing. So let me call our assembly file that we are going to write, I don't know, m.s and m.s. Okay? And what I'm going to do is write two lines here, which is start, and then I'm going to say j start, j underscore start. And what this means, I'll just tell you in a bit. Let me check if I'm copying stuff correctly, because we wouldn't want to have an oops moment. Let me just see. Right. So that makes sense. This two lines I have written correctly. Let me then now go ahead and execute all of things first, show you a few bits, and then reason about what I have done. So what I did here at the bottom was click on this plus icon to create another terminal, because we'll require two, and I am going to drag it in the editor's area. Perfect. What I'm now going to do is take this m.s and convert it into a binary, right? So let's first do that. So let me go back and then copy the commands from another window. All right, and I might actually make few errors, because why not? So let's do this. So now what we're going to do is we're going to type, actually, let me create another, text file here and first type the commands there. So we are going to have the RISC-V toolchain, and I must copy all of that and put it here. So from this, we are going to kind of invoke or call or use the GCC, right? And as I mentioned earlier, GCC is the one which calls the assembler, linker, compiler, all of those utilities internally. Then I'm going to pass it few options and those options are this, and let me take this out of our way. This means don't optimize the code, don't put your brain in it. This means, hey, whatever the binary you create, add more information to it so that GDB can understand source code related details. And again, if this is feeling like overwhelming, don't worry, over time you'll get used to it. It'll just feel like an obvious thing. This option means, hey compiler, when you compile this code, when you assemble our assembly, do not link or include the standard library. Do not include the printf, do not include that extra junk. Right? That's what this option means here. And then here, what we're saying is, hey, the architecture of the CPU that we are compiling for is RV32I, right? It's just the integer instruction set. Had I done something like this, it would mean it supports integer and multiplication instructions. The imagination you can have about this is whatever encoding, whatever instructions are generated will only be from the subset of the integer instructions. That's what it means. This MABI has to do with if there is one recipe calling to another recipe in the C language, which we'll come to, then how are the information to be passed? How is the information to be passed from one recipe to another? This becomes clear and we'll invest more time into this much later, but I'm just specifying this right now. Then what we are going to do is pass it another set of parameters. The minus WL here means, hey, whatever I'm passing after the comma immediately, that by the way is for the linker. So as you call the linker, as GCC calls into the linker, hey, pass it this LD file, and recall what the LD file means. It is the linker script, fair? And then here we will have this m.s, which is, hey, this is our assembly file, and everything else is some sort of knob or configuration that we are going to pass to GCC. Now, if you notice, we don't have the main.ld here, and I'm going to actually make it m.ld. So we don't have m.ld with us right now. So we are going to go here and create m.ld. Now, what goes into m.ld, I wouldn't want to invest time right now into that. But very quickly, I'm going to again copy paste some content here. And what is going to happen is the code is going to sit at this address, right? In the QEMU machine that we are going to use, the details of it, which I figured out from their documentation and their source code online on GitHub. So it is going to the code is going to be fetched from this address. We are saying we want to spawn our code or reserve code space worth 4 KB. And this is here is essentially saying, hey, put all the executable code at exactly this starting location. Fair? So, long story short, this is going to instruct the linker where to place or what addresses to assign the instruction against. Perfect. So if this was like, too much information, trust me, over time, this will just make sense. You won't even have to remember it, but much like me, you might need to copy and look up the commands. Okay, so I think we have the command with us. We are going to go ahead at the bottom here and paste this command. And let me actually now zoom out. Let me go to 100% here. Yes. So what I'm going to do is execute this command, and then it says, hey, there is something. Okay. So our m.s needs to have a new line here. That's what it complained about. But nonetheless, it has generated the a.out, right? What I want to do is stop calling things a.out and propose a name for the output file. And the -o option does it for me, and I'm going to call it main.elf. You can call it anything. I'm choosing to call it main.elf. So as I do that, the main.elf is available here. So this executable only has one instruction, that is this. And what this instruction is, you can take a look at the reference card and figure out, or just after the execution, I'll tell you what that is. Execution of what? Execution on QEMU. So let's then go back and let me steal another command. And the command is this. So let me paste that command right here. Let's go over that command. So what we are saying is, and let me close this. We are saying, hey, we want to call the QEMU system, the binary, the software. And then we are saying, hey, as you start the CPU, stop it at the first instruction. Don't execute that first instruction also, right? The -m means the specification of the machine that it needs to act like. And then there is a virtual machine that QEMU by default, the implementers implement, which is called the virt. And then we are saying, hey, we don't want graphics, we don't want BIOS, we don't want anything. What we want you to do is take this ELF and treat it like the executable that you are supposed to execute, and go ahead with the execution. And oh, by the way, uh, provide us a tunnel so that GDB can connect with you. And this requires some details. So we have the QEMU happily trying to run main.elf, and not only will it try, it'll actually stop at the first instruction, and the first instruction was this, right? So my claim is, this is the instruction, this is the label, which will come to this part of the assembly language syntax, and this is the only instruction. So just stop here, don't execute it, right? And our intention is also not to execute that instruction. It's just to get a system started and see what's going on inside, right? Okay. And right, I was to talk about the GDB, and what we want to do is connect GDB, which is another program used to look inside, not lick, look inside QEMU, right? So this is going to be, so to speak, our microscope, our telescope, and this is going to be the universe where things are going to get executed. All right, enough talk. Let's go ahead and then execute. So I am going to take this and put this command here. So I did copy pasting essentially, and I now hit return key, and you notice nothing is happening, and that's because QEMU is paused on the first instruction. Perfect. We go back to our next terminal window here, and then I execute another black magic command. And okay, what that command is saying is, hey, GDB multi-architecture, I'm going to start a debug session that is based on the main.elf. So use the reference from this file. This file also has some debug information, and execute this command. And what this command does is it connects with the QEMU on the port 1234, localhost 1234, and then sets a breakpoint on start, and then continues the execution. Okay, so if this sounds like a mouthful and complicated, again, don't worry about it. We'll get to the details of everything, trust me, in due time. So when I hit enter, you'll notice that it says, hey, I am on this memory location, which was the same memory location we provided here. So QEMU starts its execution from there. So that is verified. It says, okay, from the m.s, I'm on line number 2. So I'm at the point where, I'm about to execute this instruction j_start. Perfect. All right, so we have come a long way. You can breathe now. And what I want to tell you now is, if I type, we are not going to execute this instruction. This instruction, what it does, I'll tell you, but we are not going to execute it just yet. What we are going to do is do info reg. And if you see info, the output of info reg, some things will look familiar. So I talked about a program counter. So you see PC here, which is pointing to the location where our first instruction is. So that is interesting. So the program counter is exposed to us. So GDB is now letting us look inside the CPU, right? Using this command here, the GDB command info space reg. And if you see here, there are different registers and there would be 32 of those, followed by the PC here. So what is interesting here? The interesting thing is, if you go back into the reference card and take a look at the friendly names, the ABI names of registers, these are those names, the RA, SP, GP, T0, T1, all of that, essentially X0 down to X31. Friendly names. And why friendly names will come to again in due course of time. But the program counter is what I want you to be aware of and take a look at. Perfect. So what have we done so far? We have taken our assembly code, converted it into a binary, then we have loaded that binary into QEMU, and QEMU it's about to run it, but QEMU using GDB, what we have done is looked inside the state of the CPU via GDB, right? We connected GDB and QEMU, and GDB instructions are helping us look inside the CPU. Okay, and then now we're going to quit GDB. So the way to do that is type Q at the GDB prompt right here, and then hit the return key. It asks whether or not we want to quit. We want to quit, so we'll type Y, hit return, and we have exited. Now our terminal here is missing, so I'll go here and then say show terminal. Okay, the terminal doesn't exist. So I'm going to use the shortcut key Control tilde. Tilde is the key next to 1 on the keyboard. So if I press that, my hidden terminal shows up, and the QEMU is still running. So I'm going to quit that, and the way to quit that is press Control A, then release it, followed by X. So Control A, one combination, leave the key combination, and then press X, and QEMU will exit. All right, so we have come a long way. Now to the homework part. What I'm going to do is run another command, which is object copy. And object copy, so there is a backstory to that. So this ELF right here has debug information that GDB used, and GDB was able to figure out that m.s is where the source code was because of the debug information in ELF. So it has the binary code plus some extra metadata for GDB. What we want to do is strip away the metadata and just have the raw binary, just the instructions. So we are throwing away the debug information so that we can open up the file and look at the bit pattern. So, it will become so more, clear. So I'm going to say obj copy. So obj copy is the one that converts main.elf to binary format. So let me then go ahead and copy paste extra flags for it. So we are saying, hey, output in the binary format by reading main.elf, strip away, throw away all the debug information, and create a file main.bin for me, which only has the instructions lined up. So main.bin is created here. All right, once we have that, I'm going to execute another command that kind of prints the binary in the raw bits format, and that command is xxd minus e minus c 4 minus g4. These are options so that it prints it in a pretty format. We'll not go into the details of it, and I'm going to hit return, and you see that it has printed in hex the instruction, and there is only one instruction, and that instruction is this. Now the question is, what was this instruction? This instruction is a jump instruction. So what this translates to is, hey, jump to the same location as this instruction. This is a label. We could have written something like this, which means, hey, jump on the same location, which means it will execute the same instruction again and again. It's like an infinite loop. Infinite, it's like a while one without anything, if you happen to know anything about C, which I'm guessing you should not. So that's all. That's just a simple instruction. Now the homework for you was, this is hex. So what we can do is, you know, convert this hex into binary. So it's, oh, by the way, this 0 here represents the first instruction, right? So at the very start of the binary, we have this. All right, so if we have this, what I want you to do is go to RISC-V encoder, decoder, I think. There is an interesting project here. You will land on this, and then you can just pretty much, I think, paste. Yes, so you can paste the stuff here, and it will represent, you know, the instruction for you. Again, you can match up this bit pattern with the reference card and see whether or not it represents a jump instruction. Why JAL? We'll again come to that in a bit. That has to do with the fact that we have to do something like this here. Let's see. Yeah, well, the JAL, I'll reason about that in you know, following videos, but do go ahead and make sure that, you know, different bits here are corresponding to the jump instruction, and it's corresponding to, you know, jump at the same location. All right, so with this, we have seen the journey from the text file down to the zeros and ones, and hopefully you're convinced that the CPU was executing and fetching from, or wanting to execute, an instruction which was zeros and ones in the memory. All right, with this, I'll see you in the next one.